My name is Alexander Karokin from the University of East Anglia, and our first presentation is by Vernon Squire about the wave-ice interaction.
Thank you, Sasha. Thank you for coming along, and hopefully thank you for listening. I'm going to talk, well, firstly acknowledge the sponsors of this work, ONR and the University of Otago, and of course the Isaac Newton Institute. And I had already forgotten to switch the microphone. So we'll do that. There we go. Okay, right. And I also want to acknowledge my collaborator, Fabienne Montiel, who couldn't make it here, unfortunately, and is hopefully going to watch this talk from New Zealand. So, in the middle of the night, of course. Not live, but subsequently.
1:30 in the morning in New Zealand.
The other thing I want to say is this is by nature of a sort of midlife crisis talk. I did actually say that to my wife, who was sitting in the audience there, and she made 2 points. Firstly, she said, "Don't you mean a late life crisis talk?" And the second one, she said, "Or maybe it's a midlife crisis talk and you'll live till 130. So we'll get on with this. Right. Well, what I want to do is I recognize the fact that the audience was made up of people who were modelers, people who had sea ice experience, and people that had waves experience, all sorts of different areas. So I thought it would be a good idea to spend a little time, just one slide, just talking through Sea Ice 101, basically, and very elementary stuff. And I'm going to do the same thing with wave ice interaction, and also a little bit around the marginal ice zone. Mike's led into this, which is very convenient, so I can go through that pretty quickly. I'm then going to talk about a couple of paradigms. We're obviously thinking about paradigms today. My paradigms are different from Mike's. Actually, I don't think Mike knew the word paradigm before I told him about it, but my paradigms are different. I'm going to talk about the airy wave ansatz, A equal A e I kx minus omega t, and an alternative to that. And I'm particularly interested in an alternative to that when I'm looking at data. And I'm going to try and justify that alternative by talking about glacial creep, which may seem slightly strange, flow jostling, and the power law fluid. And because I'm conscious of the fact that that alternative equation there has 2 degrees of freedom, alpha and n, that we don't know, ways of choosing n that are a little bit more subtle than you might imagine. And finally, I'm going to justify this, I hope, by showing you some observations that were collected in the Arctic. So, Sea Ice 101. The first thing to say is that it's not icebergs, it's not ice shelves, it's not ice tongues, and it's obviously not land ice, terrestrial ice. It's frozen seawater. And in situ, you have to recognize that sea ice is cold at the top because of the air temperature being colder than the water temperature, and it's warm at the bottom, typically about minus 1.8 because the sea is saline. Its properties depend on the growth history. So old ice is quite different from young ice. Young ice tends to be more saline. Old ice gets rid of some of that salinity. It has a very complex structure composed of ice crystals, but also it's got air and brine and other salts within the ice. And in some circumstances, it also has organic matter embedded within its matrix. It's anisotropic, and it's also spatially and temporally heterogeneous. That's quite an important issue with sea ice. And so that means when you model it, it depends on the scale at which you're looking. Its mechanical behavior depends on strain rate, and again on spatial scale. So the big models have different constitutive relations from models that we're looking at today, or that I'm looking at here. It can appear in nature in various forms. You've seen some of the forms this morning. Primarily, I think you saw pictures of the marginal ice zone where you've got separate ice flows. But you can get continuous sheets of ice that go for tens of kilometres. And typically, those are called shore-fast ice. So you have almost constant thickness, uniform thickness plate sitting on the surface of the ice that, as I say, may stretch for 10 or more kilometres, sometimes 100 kilometres. What else have we got? It can also appear as grease ice, nihilus, which is very thin ice with highly elastic, and as we saw this morning, it can appear, particularly in the marginal ice zone, as separate flows of just a few millimetres across, which are sometimes called pancakes, to vast flows of kilometre size or more. And the marginal ice zone is, it wasn't actually defined this morning, it's defined as the region right near the ice edge, and it's kind of loosely defined as the region that's susceptible to open ocean processes, so primarily waves. Waves penetrate the marginal ice zone, we get upwelling, we get downwelling there, we get eddies formed. There was a nice picture of an eddy that Mike showed first thing. That was my picture, by the way, showing the eddy. The ice acts as a tracer. Jets was the one you get jets along the ice edge as well, as we learned from Stephanie. It exists at thicknesses which can range from just a few millimetres when it's forming up to order 10 metres sometimes. Pressure ridge is much thicker, and there's an ice called Sickersack, which is very thick, fast ice, which can grow up to 20 metres thick. And of course it may have snow on the top, and it may have platelets underneath. The crystal structure is quite variable, and the bottom is very open in terms of the presence of brine. So, wave-ice interaction. Again, Mike has said some of these things. Waves, as they enter the marginal ice zone, reduce in amplitude as they travel. And the two mechanisms, his paradigms, but I'm going to call them mechanisms that lead to that reduction in amplitude, are dissipation and conservative wave scattering, which is really about the redistribution of wave energy. Importantly, the waves break up the ice, and if they're sufficiently energetic, they can pummel the ice into a slurry. But generally, they create the flow size distribution, and they move flows around. And I can't get through this without mentioning the effects of climate warming, because that's why this area has become terribly important. Climate warming leads to weaker ice, so more compliant summer Arctic sea ice. The perennial Arctic sea ice that used to survive the summer months, albeit with lower concentration and slightly thinner, has disappeared for several months in the summer. There's been a 55% drop in the amount of sea ice in September, for example, over the last 20 or so years. We get more mobile ice flows. We get a greater incidence of leads, which are rivers in the ice, and polynyas, which are lakes in the ice. And we get a less compact ice canopy. And the other thing that's happened that's made this area so important is radar altimetry has shown that over the last 20 or so years there's been a trending up of wind speed, ocean wind speed, which has led to a trending up of significant wave height. And so we're getting larger amplitudes, particularly in the Arctic, particularly the high latitudes, and those larger amplitudes are more likely to travel further into the ice, to break it up and to pummel it. Finally, just to mention that in the summer, that pummeling and breaking up creates open water, and that changes the albedo of the surface, so it supplements what we call ice albedo feedback, and you get more and more melting. It's a sort of runaway effect, positive feedback effect. In winter, the opposite happens, of course, because by breaking it up, you've got cold air temperatures and you can actually build more ice. So that's shown in this cartoon. On the left, it's summer, you're melting the ice, you're breaking up the ice and you get more ice melt. And on the right, you've got cold air temperatures and you get more ice formation because of the waves. Marginal ice zone morphology. Typically, ice flows from about 10 to 100 metres or slightly more was shown by Mike, but we're getting a little bit more pancake ice now. And of course, the Antarctic has a lot of pancake ice, so that's typically less than a metre across. I said the ice cover is primarily created by wave-induced breakup. Mike touched on this. You need to look at where scattering becomes important. When the wave number and the flow size, the radius say, are about order 1, then scattering will be significant. But of course, if you've got a tiny ice flow and a very large wave in terms of wavelength, you're not going to get much scattering. So there is a region of periods that become important here where scattering may dominate other kinds of dissipation. But wave energy dissipation is also important. And I will come back to that in a somewhat offhand way in a moment. And the other thing to remind you of is that waves attenuate preferentially. So they get rid of the short wave energy before they get rid of the long wave energy. So long waves can travel vast distances in the Arctic. The other thing that is interesting is that shorter waves spread more quickly than longer waves. So you can actually get collimated waves far into the ice cover. And you see that here. This is a synthetic aperture radar image of East Greenland sea ice on the left there. That's the East Greenland current. And waves are coming in from the south and travelling northwards, pretty much south-north precisely. And you've got 3 spectra showing on the left-hand side in blue. And what you see there is, firstly, if you look to the right, there's a number. That's the wavelength, and you see that the wavelength is apparently changing. And you also see that the spectrum show that the waves are reasonably collimated in the bottom 2 spectra, but broader in the north one. Now, the reasons for that could be that the ice is dispersing the waves differently from open water, and so that you're getting longer wavelengths. And it could be that the long waves, or far up into the north, you're getting much more spreading of the waves in a directional sense. The other alternative to that, given that it's a synthetic aperture radar image, is that in fact we're not seeing dispersion at all. We're just seeing that attenuation of the high frequencies as the waves move north, and so the main wavelength that's being picked up by the SAR is actually increasing. So the attenuation could be, that preferential attenuation I talked about could be leading to that, that change in wavelength, and the apparent directionality change could well be due to the resolution, loss of resolution at the top there, because if you look you can't see the crests nearly as easily. So the jury's out as to whether dispersion actually occurs. Okay, my two paradigms. My two paradigms are that there are 2 schools of thought for how you model sea ice. And there's paradigm 1 is the one I'm wedded to, although this talk's actually about paradigm 2 later. And that's where you try to replicate the physics as best you can, and you accept that there are approximations in what you do, but you try to model the process that is involved in wave-ice interaction. The second paradigm is different. It's equally important. I want to stress it's a really important thing that we need to do, and that is where you're interested in putting ice in a wave forecasting model, or wave-ice interactions in a wave forecasting model such as WAVEWATCH, or you might have a Earth system model and you want to put in waves. And you couldn't possibly put a massive scattering model into that situation. You might be able to put the energy action equation into WAVEWATCH. It already has it in. You might be able to modify that, which was what Mike was doing. But it still would be computationally impossible to have a full scattering model. So what's evolved are these parametrizations where one is trying to represent, let's say, attenuation of the waves as they travel through the sea ice. And the other thing I mentioned was this airy wave mode ansatz, A equals A naught e to the kx plus I kx plus omega t. And the problem that I see there is that right from day one you're assuming linearity, because that naturally gives you an exponential decay. And I want to be able to deal with data in a more broad in a broader sense than that. Okay, so let's do some examples of paradigm one. Well, the hydroelastic models that have developed over the years, going right back to, in fact, the previous century to the last one. The elastic plate model was devised by someone called Greenhill in the 1800s, late 1800s, and that's been used consistently. But the models have obviously become more sophisticated over the last 100 years or so, and now we're able to deal with waves going into continuous ice, work out the reflection coefficients at the edge. That was done by Fox and Squire back in 1994, but also put all sorts of features into the ice, and Tim Williams, who's in the back there, did a lot of that work. Well, you might want to look at waves crossing a crack in the ice, a lead, a pressure ridge, a change of thickness, a change of material property, maybe a change of Young's modulus, all those kind of tweaks on a basic model of wave propagation. But the important thing is that the ice is essentially continuous apart from those irregularities. A second example of that is waves travelling through grease ice or pancake ice at high concentration, where you might choose a viscous or a viscoelastic layer type model to represent the propagation. A third type, which you may not have thought about, is the marginal ice zone, where you have lots of flows and you're looking at wave generation or something within the pack. And you might even not even take into account the elasticity of the ice in that situation, because that's not the primary thing you're looking at. So the important thing is that you're assuming some kind of plate model, typically a thin plate, a Kirchhoff-Love plate, or a Euler-Bernoulli beam, or a viscoelastic layer, and you're plugging into it some sort of shear modulus or Young's modulus and a viscosity, and then you're cranking it up to see if it replicates what you observe. And I'm not saying these models are 100% accurate by any means. The issue that I'm raising is really the fidelity of the parametrization. So this is an example of that kind of model being used in the Arctic. What we have here is a very long transect of the underside of sea ice. Where does that come from? It comes from a submarine. Submarines routinely go under the Arctic, or used to, and they're routinely looking upward with sonar to see what the underside of the ice is like. Now, that was originally because they like to come up sometimes and fire missiles, I suppose, so they want to know what the thickness is like. But it's a wonderful tool for looking at what the profile of sea ice looks like on the underside. You can use isostasy, and because sea ice typically is about 7/10 underwater and 3/10 above, you can see what the thickness looks like. And down here, I've done that for a little section, and you can see that's what the ice looks like. And I think that illustrates that ice is not a very thin, uniform plate. It's quite uneven. These things here are pressure ridges, so that's the keel of the pressure ridge, and that's the sail. And there's lots of pressure ridges over that distance there, which is just 130 kilometers. So I've done that for this whole section of 1,670 kilometers, and we use a 1D scattering model to work out what waves do as they travel through that. And that's a 22-second wave traveling through that ice across the full nearly 1,700 kilometers. And just to show you what it looks like zooming in, as I said, that's the thickness itself, and that same 22-second wave is trundling through that ice there, and you can see that it hits that pressure ridge and the amplitude increases, and then it trundles a bit more and it gets into a rough area and the amplitude increases. This area here is either very thin ice or a polynya. Remember, a polynya is a lake, and you see there's no reflections occurring, it just goes straight through. And obviously you can do that for different periods, and that's what we've done, and we can then find out what the attenuation coefficient does in terms of period. Again, that's something Mike mentioned. We don't get the t to the -2 behavior here. I can't really explain that. It's a theoretical model, and it's thrown up a different dependency, which is actually exponential, roughly. it's further, it's much longer periods than Mike was looking at as well. So there are a couple of reasons why it might not represent a t to the 2. And t to the 2, of course, is only observational anyway. So another example is paradigm 1 in the MIZ. This is the physics-based one where you try to pin down the physics of the individual process. You can do 1 or 2D scattering and have a look at wave-induced breakup reasonably well. The issue really is this one, the second bullet there. We are hopeless at actually pinning down what the dissipation is, where the energy goes. What we need somebody who really understands oceanography to solve that problem, because there's a lot of energy lost in the water column. Sea ice inelasticity, I think, is a second-order effect. I don't believe it's going to play much of a role, but the turbulence in the water is getting rid of a lot of energy in waves. The interesting thing, of course, is that paradigm 1 does fit very well doing field experiments and laboratory experiments. So another example here, this is a scattering model. Up the top there you can see we've populated an area of the marginal ice zone. We put it into 2 zones. We've randomly thrown in a very high concentration zone of flows which satisfy a size distribution on the right there, and a slightly more open, less compact marginal ice zone on the left. We tried it again with several zones within the marginal ice zone, and a feature that's often seen is a zone at a low concentration near the ice edge of relatively similar size flows. And finally a band. There was a lot of interesting bands in the late 80s. These are features like the jets and the eddies, etc., that form off the ice edge. And we can take a distribution like this and we can work out what the attenuation coefficient does as a function of period. And that line there is typically roughly t squared. And interestingly, this shows the spreading. There's less work done on spreading, but it's the distance to a completely isotropic sea. So an isotropic sea is where the waves are going in all directions, and what it shows is that the distance to isotropy depends on period as well, and the shorter period waves, up to about 10 seconds, reach isotropy very quickly, but then there's a sudden increase in the curve here, and that means that the longer period waves probably will never reach isotropy, so they'll go through the ice in a long crested way. And just to show that we do compare it with data, this is the data from the band experiment that was done. That's the waves coming in, that's the waves after they pass through the band, the dark curve there. And what we tried to do is to replicate what the waves would be like after they pass through the band. We plugged in some viscosity to see what that would do in that scattering model. And it turns out that you don't actually need much viscosity to replicate the energy loss in the band in that particular situation. And that one's spreading as well. Okay, so paradigm 2, this is where probably the easiest way to describe it is to start with an example at the top. So here the marginal ice zone is represented by a viscous ocean, right? The whole ocean is viscous compared to an inviscid ocean outside. So when the waves go in, they're subjected to viscosity, which is conveniently called eddy viscosity, which gets rid of their amplitude to some extent. And that's one possible type of model. Another model is taking the continuous ice model, which is the one I have showed you earlier that we ran right the way across the Arctic, and saying, well, if we change the values of the shear modulus and the viscosity, if we've included viscosity in it, we can actually use that to represent what's going on in the marginal ice zone. The same is true of the viscoelastic layer model. You can choose values for G, the shear modulus, and mu, the viscosity, and somehow that represents what's going on. Now the problem with that is we should really be checking things like the attenuation coefficient in terms of frequency, the stuff that Mike talked about, the t-squared stuff. And really, if you're going to split up a continuous medium in terms of lots and lots of separate flows of the same property, then you should be using homogenization theory. So, and that's hard. I mean, there's no doubt it's hard, but it's primarily hard because the ice doesn't break itself up into two media, it breaks itself up into many media. So between the ice flows, there are other kinds of ice, such as brash and slurries of grease ice. So the biggest problem with this type of model is to find the G and the mu. And the only way you can do that is to actually go out in the field and measure attenuation, and then you move backwards and you best fit your model to the data. And of course that immediately means that the G and the mu have no physical meaning. And it also means, as I will show you in a moment, that the G and the mu can vary quite widely. Mossig and colleagues actually summarise this in the context of the continuous ice models. Firstly, they're really meant for continuous ice, so their use for other ice media, such as the marginal ice zone, is really not correct. The viscoelastic layer model and the thin beam model are both really continuum models, and they are different and they produce different results, but they're actually quite similar in some respects, as I'll show you in a moment. The thin beam model, which is used for continuous ice, predicts a single propagating mode and one complex mode in the first quadrant, whereas the viscoelastic layer model, which is a very clever model, permits flexural, longitudinal and surface waves, because it's actually replicating a material that can allow those sorts of waves to exist, but a marginal ice zone can't. So another thing that Mossig pointed out is that G and mu can range far and wide in parameter space, particularly for the thin beam model. We can get values of G, the shear modulus, which are equivalent to titanium. So you've got a marginal ice zone made up of separate flows where you're saying that it behaves like a coating of titanium on the surface, which is obviously a little hard to accept. And the justification for that in the context of that thin beam model is that somehow we're parameterizing all those other dissipative mechanisms that occur within the ice. Finally, I just want to mention that nobody's actually observed, and I touched on this in the SAR image, nobody's actually observed that dispersion occurs within the marginal ice zone. The jury's out. There's some data which even suggest rather than an increase in wavelength, you get a decrease in wavelength. This is the plot I was mentioning. Oops. This is the plot I was mentioning, which shows this is the thin beam model, and this is the viscoelastic layer model. And you can see that it's a very, very rich, complex plane with lots and lots of roots there. And it just makes it difficult numerically to find the propagating wave. This is chosen so the propagating wave is very near zero, just for convenience of plotting. But no. But you see they're actually, the two models predict the same propagating wave. But numerically, hard to distinguish between these because these roots move all around the complex plane for different inputs of data. Okay, I'm going to move right along because I want to get to some data. So what can we do if we actually want to analyze data? Well, what I'm proposing is that we use, instead of using this standard exponential model for attenuation, that we put a power n after it. That equation there, that differential equation, has a solution. It's well known. It's nonlinear, but the solution is well known. And when n is 0, you get a linear law, a linear decay law. And when n is 1, you get an exponential decay law. And of course, everything between the two. So it looks like that. You can put n is any value you like, and you get different kinds of attenuation. But is there any justification for that? Well, the early justification was back in 1973, when that model was tried out with n equals 3. And n equals 3 is the Glenn flow law. which is a flow law that's used for glaciers. And I have to say it's fairly unlikely that waves travelling through sea ice have an n equals 3, because the strain rates in those two experiments for a glacial flow model and waves travelling through sea ice are very, very different by many orders of magnitude. But the same equation emerges if you do a back of the envelope calculation for granular flow, using granular flow theory, when the flows are small. So we're talking about pancake ice primarily, or I guess if the waves are very long. And what you essentially get is a stress strain rate law where the viscosity, mu, depends on strain rate. So if that dot was missing, if that bracket was missing and mu was a constant, that would be just Newtonian flow. But I'm going to propose a law where we've actually got a mu which depends on strain rate. There it is, there. And what that says then is if the value of n is outside of the 0 to 1 range, domain, then the strain rate decreases, the viscosity decreases, the strain rate increases, and so the material is said to be pseudoplastic. If it's inside the 0 to 1 domain, then the viscosity increases with increasing strain rate, and that's what we observe. So what we observe is that shorter period waves reduce in amplitude more rapidly than longer ones, and that's essentially saying the same thing. So the process, as opposed to the sea ice itself, exhibits dilatancy. And what that means is it's shear thickening. So when n is 0, the strain rate is constant and mu increases linearly. If it's a half, mu increases linearly, and n equals 1 is the exponential case. And then you can start to play around. If you have a dispersion relation that gives you, like this one here, which is a constant viscosity, eddy viscosity model, you can get that the attenuation coefficient should go as omega to the 7/2. So let's adjust mu to bring that down to what's observed. Let's assume that we see t squared, t to the minus 2 rather, which is omega squared, and you can bring that down to get that omega squared by setting n equals minus 2. So that tells you what kind of attenuation you're going to get. But we don't necessarily want to use a dispersion relation. And so can we do something that doesn't require a dispersion relation? Well, if we look at the tail, I'll show you this later if I've got time, we find that the energy density in the experiments I'm going to present goes as omega to the minus 3. And so can we tune this equation and get n so that we can actually replicate that omega to the minus 3? And you can. You can actually choose n and get the coefficient such that we can get alpha is omega squared, which was that challenge we set ourselves if we set 7/3. I mean, I'm sort of on a roll here. It's all a little bit hand-wavy, but you might go out and you might measure strain rate. And suppose you measured strain rate on ice flows within the pancake ice and you discovered that they went as omega to the 6. Well, that's just taken out of a hat. I mean, it's not a figure that you expect to see. If you actually look, you say, well, strain is proportional to omega to the 4th, and then you divide by t, so you end up with strain rate being proportional to omega to the 5. But we've measured omega to the 6. Can we choose an n to produce omega to the 6? And you can. You can choose n is 5, 6, and you get omega to the 6. But someone's then going to say, well, the amplitude in here actually changes with omega 2 because it's up here. So can we build that in? And you can. If you make a change with omega, then it changes n slightly, but you can recreate omega to the 6 again. So what I'm really saying here is, and it's all very non-rigorous and very early stage, is that you can actually take that model, that power law model, and reproduce some of the information that you might be seeing in observations in a somewhat more subtle way. So here's the observations. Right, an experiment was done in the Arctic, in the Beaufort Sea, back in 2015, around October time. And this was the first experiment they did. There was a whole bunch of wave buoys being deployed, and those wave buoys were tracked for a couple of days. And what I've done here is there's the significant wave heights at each of those wave buoys, looking into the ice cover, and I've just plotted that significant wave height along the transect for a particular time. And the same for the other wave buoy. The blue ones are the swift buoy, and the red ones are another buoy which is based on accelerometers. They do actually produce slightly different results, which is interesting, and people are talking about that a little bit. The swift buoy tends to be filtered at higher frequencies, and the wave buoy don't. So they do produce different results, but that's not what I want to talk about here. So we've got the decay or the attenuation of significant wave height with distance from the ice edge. And you've also got a change in the spread showing there. This again, it just shows the difference between the swift buoy, which is the blue significant wave height, and the red, which is the wave buoy, as along, this is time across the duration of the experiment. And the values of alpha that you would extract if you were trying to fit an exponential curve to it. And interestingly, if you try to fit the n model to it, what values of n do you get? Well, the values of n you get for significant wave height are either 1 or 0. That's where they're clustered. 1 means exponential decay, and 0 means linear decay. But that's significant wave height. And of course, you can just do a little bit more analysis of that, and this is the probability of linear attenuation, so that's the n equals 0, and you see that the probability increases with amplitude. So as the significant wave height goes up, the probability of the attenuation being linear goes up. Just moving right along. This is the actual frequency data now. This is not significant wave height, this is frequency. So we've got frequency on the left, and this is a spectrogram. So these are all spectra running vertically. The yellow is high and the black is low. So you're getting high waves around this 0.1 area. So mostly 10-second, that's where most of the amplitude is. I'll focus on the swift because it's easier to interpret. The beta value, which is the attenuation coefficient, pretty much in that range of 2 to 4 to 6 possibly times 10 to the minus 5. Very low attenuations because it's pancake ice. And then the n value, you see the difference in color. The black seems to be associated with the low values of frequency, and the lighter colors with the high values of frequency. I'll jump over that. That's spread, and it's very small. So this shows pretty much the same thing. What we see here is the value of n compared to the energy. So you can think of that as the amplitude, if you like. So when the amplitude gets to 1.5, 2 meters, suddenly there's a massive jump from 1 down to 0. So what that's saying is big waves decay linearly, big high amplitude waves. Low amplitude waves decay exponentially. And we see here, this is the percentage, hang on, median n. Okay, so that's showing against, oh, I can't remember what that one is. Where are we? I'll go to this one, percentage linear decay profiles, and you can see that the percentage, the probability that you're going to get a linear decay increases as you go to the right here. So this one here, which I jumped over, is frequency. So there's a dependence on frequency as well. So what we find is that when the frequency is low, we're likely to get linear, and when the frequency is high, we get exponential. The data are very nice and clear. They form into two bands. So we find that the E0, which is the energy density against frequency, is roughly a power 3, which says something about the tail of the spectrum, and 4.8 here, particularly at the tail. And at lower frequencies, it goes over. It just curves over, so there's less energy there. And that's our beta curve. It's coincidentally, it shows exactly what Mike said, F2, so it's omega 2, t to the minus 2, which means it goes as wavelength. So just closing off, I see I'm almost at time. So what we find is in the data that the shape of the attenuation curve is not always exponential, and that the curve seems to depend on whether on both the wave height and also on the wave frequency. Interestingly, I haven't pursued this very much, but the power law fluid, I did say this, with n equals 0, has the strain rate as constant, which means that AW has to have a particular functional form, and we're looking for that at the moment. So we look at the strain rate and see whether it's essentially unchanging. I'm looking at whether a power law fit to energy density as opposed to amplitude might work better, but the jury's out on that. We've calculated the exponential decay coefficient, it's that, and we've also calculated the amplitude decay coefficient. You've got to be a little bit subtle getting that value because of the move from energy density back to amplitude. And finally, I guess the key message from this is that the Airy wave mode ansatz may not be the best point to start a parameterization of waves in ice if you want to ultimately analyze data, because if you're going to get linear decay, it's going to throw up some problems. And I guess I'm saying that in a very preliminary way, you know, maybe we should be using a slightly more general model, dA by dx equals minus alpha times a to the n, or the energy equivalent to that in wave forecasting models such as WaveWatch. What we would have to do first, though, is to accept the fact that dispersion is irrelevant. So thank you very much.
Thank you, Vernon. Yes, please. Yes.
Yeah, I think it's very interesting that the data showed n is either 0 or 1.
So do I.
Yeah.
Well, I must say I'm not the first person to see that, because Alison Cahoot and Mike, when they first analysed the Antarctic data and looked at significant wave height, found linear decay.
Yeah, but I have a second part of the question. But there's maybe another way to explain. Is because the wind input.
Oh yeah, absolutely, yeah.
That's all.
Yeah, yeah. No, I mean, I mean, there's all sorts of things you can plug into it and say, well, it can't be that because of this. This is it's a very basic model that will ignore some of the physics in it. But, you know, all I've done is analyze the data and said, it's interesting that I see linear decay and I also see exponential decay. And we're trying to pin down at the moment, literally I got some plots this morning trying to pin down exactly what's causing that difference. I don't see much between the two, so all that fancy stuff of choosing n at the beginning was kind of irrelevant, because I can't get 3/5 and 9/6 and all those other values, but I can get 0 and 1.
John, please.
Yeah. I have an immediate reaction to your first point there. I think the linear theory or the weakly nonlinear theory is an excellent starting point in such an analysis. That you will come very far. I've done experiments and theories, of course, but you will come very, very far in investigating what's going on under the ice. That is a lot, of course. The boundary layer effect has a lot of processes, but you can do it systematically with linear with a weakly non-linear theory as a starting point, and that is cleaner and easier, and just follow the routes which Mike Mayland spoke about. That's it. The other way may be very troublesome.
Mike, please. Yeah.
Just one sort of caution, because if you use significant wave height,
But I didn't in the last part.
yeah, it's a proxy for period.
Yeah, I know. I mean, I understand significant wave height has its problems, and that's why we did it across all the frequencies that were present. So, and I mean, you and I have had that conversation. I understand that significant wave height won't work, but you know, as a first step, it's worth doing to see what happens. But you know, the analysis shows, without too much ambiguity, that we do get linear decay when we increase beyond a certain value for the amplitude at a certain frequency.
Daniel, please. Yeah.
So you suggested that n may not be equal to 1. One fortuitous example was the pancake jostling. Okay, at n not equal to 1. Earlier on, you said that you reckon most of the dissipation is due to the ocean, not inelastic.
Yeah, absolutely. Yeah, I mean the model that I proposed is a parameterization of everything. So the idea is that you could use it to replicate the behaviour of dissipation as well, less scattering.
So if you talk about energy going from the eddies in the ocean, okay, are you thinking, this is just an opinion here, are you thinking due to effectual deformation of the flows, or are you thinking of the flows moving around and that generates
No, I'm
eddy
thinking of
motion?
flows colliding.
Okay, so that actually generates eddy motion. That generates a length scale of motion, doesn't it?
Yeah.
Length scale for the eddies. So you could probably maybe.
But these flows, these are pancakes. They're very small. They're, you know, this sort of size. They're a lot less than the wavelength in terms of diameter. I'm not talking about big flows here.
But it tells you the length scale at which you're putting kinetic energy into the turbulence in the mixed layer.
Yeah,
So that may be a way of backing out
absolutely.
some justification of what N is.
Sure.
Oh, so we should stop. Thank you very much, Vernon. And,